taken this computational matrix, I brought it back down to moments of computing moments of order 2n. So I've got twice the degree, but now I can do this in complexity order 2n to the d plus 1. That's going to be better than order n to the 2d. We were getting very excited at this stage. This is great. We're going to be able to compute the mass matrix in order n to the d plus 1 operations. But then we realized something's wrong, because optimal will be order n to the 2d. This is too good to be true. What's going on here? But nevertheless, that's what it seems to be. If I calculate those, it's correct. It's order n to the 2n to the d plus 1. So I can get all of those in order n to the d plus 1 operations with a worth constant, but it's not degenerating with n. The problem is that you've got to calculate these. Remarkably, the dominating term in the computation of the mass matrix is not the computation of the moments, it's the computation of these multinomials. So what we've done is, this is the usual issue is all these integrations with funny data and so on to get the entries in the mass matrix. The leading term, the dominating term in our algorithm is going to be the computation of that. Remarkable. All right, so that's what I've said there. And it's the multinomials that dominate the cost. So if you're careful about how you evaluate this multinomial, what's wrong with just evaluating it explicitly? Well, I invite you to go away and do it. You've got to calculate all the multinomial coefficients needed for that factor there. You write a code and see how long it takes, and then try and figure out a way to make it order n to 2d. It's not a big issue, but you convince yourself very quickly that that is the dominant term. So we can compute those in order n to the d plus 1, and then we have an algorithm for evaluating these multinomial coefficients, which is order n to 2d. Everything that's optimal.